when you are solving your question, when you are solving question. Actually, not, I think that. Okay, if you can solve question in the homework, I think you don't have any trouble in final exam, in my opinion, because my questions, it's little bit lighter than the homework question. Probably, mostly, I prefer a little bit harder question in homeworks. In the exam, I am asking a little bit easier question. So if you can solve a question by yourself, okay, I think you can be happy because you don't will any trouble in the final exam, hopefully. Okay, let's start with our last chapter. I think that the next week is the last week, isn't it?
Exactly.
Yes.
Okay, very well. Okay, next week I am planning to solve one more question about the chapter 14, and I want to conclude our course. Okay, we will discuss about course next week. First of all, I want to remind you the chapter 14. I have already uploaded to video about the chapter 14, and also I shared two course lecture notes. First of all, I want what is the meaning of the energy and work. Maybe you can remember the dynamic course in high school. You know, to work means that force time displacement or force time to length. In other words, and if our force depends on to this length, okay, distance, okay, we need to multiply by the f times the infinitesimal dx, and we have to take the integration. This is the general formulation of to work. So did you take the dynamic course from me or from other instructor? I think yes. Did you take? I think silence meaning that? I can't remember. Yes or no? I don't know. Okay, yeah, maybe you can remember it from high school. So this is the formulation. What about in strength of material? What is the meaning of the work? Because our structural members does not go anywhere. But we know that our structure members are deformed. So that's meaning that they can absorb some energy. And how we can conclude this energy, if we find the displacement, so we know the internal force, so multiplication of the displacement time internal force, so we can compute to energy or work done by internal forces. Okay, so how we can compute this? So first of all, we need to find the force displacement relationship. How we can find? Maybe you can remember to mechanics of material course or to material course. If we assume always our material force displacement relationship is linear, because we define that these curve is linear, so modulus of elasticity defines between the force displacement relationship. So I can draw like a linear curve like this. So maybe you can remember from the mathematics. So integral meaning that what is the meaning that to area of two linear lines. So this is a triangle. So if we compute to the integral, in other words, to internal energy or external energy, we can say, this is the force times displacement. These do I'm sorry that this is, we can remember that the stiffness. Okay, so K times stiffness. Maybe what is the meaning of the K? Do you remember? Maybe you need a small help. Okay, let me a few seconds to open my cell phone. Sorry that I forgot to prepare to whiteboard. Let me a few seconds. Do you know what is the meaning of the stiffness? You can say yes or no. I think no. Yes, very well. So stiffness meaning that if the force displacement relationship is linear, we can define stiffness meaning that division of the force by displacement. So F times delta. So we can write the F is equal to K times delta, stiffness times delta in the formulation. So, you know, in other words, we can delta meaning that the displacement. So in integral term, I can say d delta. Integration of this term, we can compute 1/2 multiplied by K times delta square. Okay, this is the formulation. And also I have to prepare my webcam. So I need to open my application. Webcam now. Yes, back. Wherever my Wi-Fi is. Yes, there. So let's start. Sorry for waiting. Okay. So I think you can see the whiteboard. First of all, I need to clean my whiteboard. A little bit soon. Yes, this one is better. Okay. My whiteboard is ready, so I can continue. So external energy or external work done by the external force, we can compute 1/2 P times delta. So our assumption that displacement relation, the force displacement relationship is linear, so we can assume as K. So this is the external energy. What about the internal energy? So our forces, we can represent forces as internal forces. So, you know, our internal forces always changes of the area to area. Therefore, we can first of all compute infinitely small element of the area. So we are taking the infinitely small element. In this element, we don't think about the forces. We have a stress. In other words, force times, the internal forces generated in unit area. So we can write sigma or stresses instead of the forces. So displacement, we are writing the unit displacement. So our formulation changes to sigma times epsilon over 2. Okay, you can also, I don't want to go in detail. By using this relationship, this is the small element, so we taking to volume integration. After volume integration, I can prove how we can compute to strain energy. We can categorize the for categorization, axial load, this formulation. Okay, from the bending, we obtain this formulation. From the transfer shear, we obtained this formulation. Okay. For torsion, we are obtaining this formulation. First, we'll look at our structural member. This structural member is only resist to axial load. We can compute the internal energy by using this formulation. For other internal effects, we compute the other internal energy. If we our structural member resists more than one internal effects, we can add all or add these effects. Okay, for example, if we have both bending and shear, we can compute bending energy and transfer shear energy, and we can sum these two terms. Okay, do you have any problem? As a result, look at the formulation and apply the result. Just that, okay? Let's start with, I think that we can also have, okay, also I want to give one more energy. How we need this energy? By using this energy, we can compute the displacement. How we can compute the displacement? by using the conservation of energy. Maybe you can remember from high school or dynamic force. So internal forces, internal energy should be equal to external energy. So we know the external energy is equal to 1/2 P times delta. So internal energy, for example, axial load, we can compute like this. So we know this. We can, if we compute the internal effects, okay, we can find the internal energy. So we know the external force. Just only one term is unknown. This is the delta. By using this relationship, we can find the delta value. Just it, okay? Like this formulation. From thrust, we are using this formulation. From B, we are using this formulation. From moment energy, bending energy, we are using this formulation. If we just only to moment exposures, we are compute to external energy by using this formulation. And I didn't prefer to write for the shear and the torsion. Okay. Similarly, we can use to find the torsional effects and shear effects. Okay. Do you have any question for this? Again, we will apply the formulations. Did you watch the video? Offline video?
Yes.
I am not sure. Sorry? Yes, no?
Yes, yes.
Yes.
Yes. I'm not sure this is clear or not. If this video is not clear, okay, I can a little bit explain. Or if you have hocam, I don't clearly understand this subchapter. Would you like to re-explain in here? Okay, I can explain for you. First of all, I want to say because in offline video you don't have a chance to ask a question. Therefore, this is a good time to ask a question. So if you have any question, also I explain in detail all these terminations. Therefore, I don't want to lose time so much. Just I'm saying that we are applying the formulations. Okay. Okay. I think we have to make a practice to understand finding the displacement. I have, where is the example? Prefer this, like 14/25 or 14/28. Which one do you prefer? And I want to ask, okay?
25 olsun hocam.
Okay, so you choose the 14/25. This is easier than this one because you know how many 1, 2, 3, 4 diagonal or vertical elements, so I can easily compute these these member forces. So I think this is also easy, but this is a little bit easier than this one. You prefer the easier one. Okay, you know, first of all, I want to read the question. I think you can read the question too. Determine the horizontal displacement on point B. Okay, the question is this. And also material property is given A992 steel bars. That's meaning that modulus of elasticity is equal to 200 gigapascal. Okay, all the members contains this material. Each of cross section also have same cross sectional area, and also given is ready 2,500 millimeter square. So E is given, A is given. This is the truss member, you can see. So maybe you remember that from the static course, for truss members, all members can resist only to axial force. So while using the conservation of energy principle, in the question also, they ask that to horizontal displacement. So in order to find the horizontal displacement, I can use the conservation of the energy principle. So first of all, I need to look at which formulation I need to use. First one, second one, or third one. I think you can see the first one. Therefore, I look at this like P is the external force. I'm checking on the example is given. You can see 15 kilonewton. Okay. And also I'm looking to slide. So delta is the needed because this is the displacement. Okay, and what is the n meaning? That maybe I didn't explain for you. The n meaning that the internal forces, or in other words, to member forces of the truss members. Okay, member force of the trusses. So first of all, I have to find all member forces of the truss structure. So how is it? If we first of all, I need to check this is a statically determined or indeterminate. I think it's statically determined because this is the roller support, this is the pin support. I can find, in my opinion. So also in the formulation, I need the modulus of elasticity is given, area is given, every information and all the information is given in the question, so I can compute. First of all, I need to find two n values. So how we can find? By using our static knowledge. Okay, let's start with drawing to shape in here. Did you like the static course in first year or second year? I can't remember. I hope you liked, because in mechanics of material, in design courses, always we need a static information. Therefore, I remember that like 15 kilometers, but like I'm here. This is I remember in point B. This is A. This is C. This is B. First of all, I need to draw the free-body diagram. On free-body diagram, I can write just only forces. This is the force 1, like C for C. Like this is the D1 and Dx. You can see sigma Fx equal to 0. We have just only two forces. You can see Dx is equal to 15 kilonewton. And I can take it in here. So this is the 15. I can write this one. Okay. And so I need to compute again. I need to take the moment on MD. I take the counterclockwise is positive. Like what is the dimension in here? This is the 2 meter. This is the like 105 meter. Like this. Okay. So like first I need to start with the C. C times 2 is it minus because it is rotating to clockwise direction, plus 15 times 1.5 meter. This is the clockwise direction is equal to 0 because these two forces does not generate any moment because these forces pass through the point D. So I can find C. C is equal to like 22.5, half of the 22.5. I can like that 11.25 kilonewton. I compute in my brain. Okay, I think this is correct. Okay, so I found to C is equal to 11.25. So I need to find the dy by using the sigma Fy is equal to 0. So we can see that I'm taking this direction positive, like this force and this force just only. So I can by using, I found dy is equal to minus 11 times 25 kilonewton, minus meaning that the direction is downward. Therefore, I need to change to direction and I write to this value is 11 times 25 kilonewton. Okay. So I found two external forces or reaction forces. Now I can pass to the our member forces. First of all, I need to start with the point B. Okay, I'm using two method of joints. Did you remember the method of joints? Do you remember? I think yes. I'm using method of joints, and I want to start with the point B. On point B, I'm taking. My assumption is all the forces is tension. Therefore, direction is like this. This is the force AB. Okay. Now, internal force AB. This is the force BD. Okay. So just only force, one force, 25 kilonewton. You can see like sigma Fx is equal to 0. Just only two forces available. So you can easily see FAB is equal to minus 15 kilonewton. Meaning that my assumption is reverse. You know, my assumption all the forces is tension. So if we obtain to negative, so I can say the force AB is compression member. Okay. So also you can see sigma Fy is equal to 0. This is the FBD is equal to 0 because there is no force on y direction. Do you have any question for this? So I can write like in here, like 15 compression, 0 member. I write in here. Okay, very well. So I change my point to, I can continue with the point D, I guess. And we write to these forces, you know, in here, like F, CD, this is point D. Okay, this is the FAD. So from here, you can see point FBD is available, but this is the 0 force, you can see. So I don't need to write in here because there's no force available in here. So I don't need to write the FBD. First of all, I need to find this angle. This angle is alpha. You can see this is 105. 2 is 345 equation. So like this is alpha. Sine alpha is equal to 0.6. Cosine alpha is equal to 0.8. Maybe you remember from 3, 4, 5, 8 example. So I can write in here. So I think I should write there. So let's start. So this is the. Is there any external forces in here? Yes, I forgot. Sorry that this is a 15 newton in here, and this is 11.25 newton is downward. First of all, I want to start with the Fy is equal to 0. So, like I'm taking the upward this direction is positive. FAD fine sine alpha is positive minus 11.25 is equal to 0. So FAD is equal to 11.25 divided by 0.6. I think I can compute in here. Where is this? I cannot find in here. AD. Yes, I already find AD is equal to 18.75. If you have a calculator, okay, you can check to my computations. Maybe I can make a mistake, but in my opinion, this is correct. Okay. So sigma fx is equal to 0. I'm taking to this direction is positive. Like I'm looking at these forces, you can see minus fc goes in this direction plus 15. And again, you can see, so also I forgot that this is the positive, therefore this is the tension forces. I already forget to write the value. This is the tension times, okay, like I already compute the F80, so F80 times, I know the F80 times cosine alpha, okay, this is F80, this cosine alpha is equal to, these are any forces I forgot, 1, 2, 3, 1, 2, 3, yes, equal to 0. By using this, I found this FCD is equal to, if I computer is now in here, let me a few seconds to compute. I obtained FCD is equal to 0. Is it true? Did you compute? Yes.
Yes, it's true.
0. 0. This is the 15. Actually, I forgot, like, this should be minus in here. Sorry. This is minus 15, positive 15, so this is equal to 0. So this is the 0 member. This is the 18.75. This is the tension. Just only one point remaining. I don't need to write the point A because I have already computed this force, and this force. Just only this force is remaining. Point C, in my opinion, is a little bit easier than the point A. So I need to continue with the point C. On point C, just only, this is the external forces, 11.25 upward. Okay. And also I don't need to write to internal force FCT because this value is 0. Just only one force is remaining. Like this is the upward, like FAC. So this is the point C. Is there an additional force? I think no. So I can write just only sigma Fy is equal to 0. So you can see FAC is minus 11.25. So that means that this force is compression. Also, this element is compression element. So I write to 11.25 compression. Okay. I think this is a good practice for method of joints. I think that. Did you remember all the details of the method of joints? I think yes. So I find all the values, so I don't need these details. I can erase. Now I can pass you our general formulation. I'm looking at my slides. 1 over 2 p delta is equal to I write information here. 1 over 2 p delta is equal to integral n square times L divided by, like, I can use the I notation, I E times A. What is the I meaning that? I is equal to 1 to number of members. Okay, so we know 2, 1 over 2, well, we know the P is equal to 15, you can see, but we don't know the delta. And I want to start with the first member. This is the first member, this is which one is the second? Like this is the second member, this is the third member, this is the fourth member, this is the fifth member, okay? Like this is the member ID. Also, I can easily compute the length, okay? You know, length of this member is 2 meters, length of this member is 2.5, 1.5, 1.5, okay. Let's start with the first member. I'm writing the formulation, 15 square, you know. Also, you can write the minus 15. It doesn't matter positive or minus term because we are taking this square term. Therefore, the energy is always positive. Maybe you can remember from the dynamic course. Okay, so it can, you know, compression or tension terms does not matter for the computing to displacement. But I want to write the minus like times L. You can remember that the L is equal to 2 divided by modulus of elasticity. Oh, first of all, which units I can work with. This is the, I want to write start Flemington millimeter, okay? Because the and Flemington millimeter meaning that Flemington divided by millimeter means the gigapascal. So I want to write these units. So I can write 2000 for length, okay? Modulus of elasticity, you remember that 200 gigapascal. Area is given in the question. I can't remember. Do you remember? Also, you can't remember too. Like, what is that? 2,500 millimeter. So I can write 2,500 millimeter. This is the first member. Let's continue with the second member. And plus, just everything is summation. 11.25 square times length is 1.5 meters, so I'm converting to millimeter. Divided by same value. And continuing here, plus, what is our third member? This one. Times length is 2.5. I convert this one. 300 times this one. And I don't need to write the fourth and fifth members because you can see the forces is 0. So, you know, this term is 0. Maybe I can write the 0 in these terms. In other words, these forces does not absorb any energy because these forces do not take any forces or resist any forces. Okay, so by using this term, I think I need to use my calculator. Where is this one? Let me a few seconds. If I computed correct, I found this is equal to, like, this is this 7.5 delta is equal to 3.0375. I hope this is correct. Okay. So by using this, delta is equal to 0.405. So you remember that we are working with millimeters, so unit is. Hopefully this is correct. Okay. Maybe you can make a cross check for these computations. Okay. Bakıyorum. I think maybe I did a mistake somewhere in there. Actually, I made a mistake somewhere. You can see in here I forgot 2, but in formulation I forgot to write 2 in here, isn't it? So this is the half of this one, not this one. Sorry that. Right. This is not this one. This is. I forgot the multiplication 2 in here. This is 1.51875. And by using this one, I will compute. This is it. 2025. Did you understand my mistake? I forgot the 2 term in the general formulation. Please do not mistake like me, okay? You can compute 2 times larger displacement from the reality. Okay, do you have any question? Is it seems to be, is it clear? I think that clear. If you remember the statics, just we can apply the rule. From beam, we have same rule, okay? We will apply same thing. If you can remember that to, how can I say? If we can remember that how we can find the moment formulation, okay? You can easily compute this integration. And again, we can apply same rule and same thing. Just only I want to remind that maybe you can see, you know, they need a displacement on joint B and also force is exposed to for point B. What about in the question, the displacement of point A is needed? How we can compute? Or can we compute by using this strategy or not, first of all? Do you know this? Okay, I can answer this. If in the question another displacement is needed, such as A, okay, we cannot compute by using conservation of principle. I need to find another strategies. This system is just only work when the forces exposes to needed displacement. Okay, for our external force, or is there is any more than 2 forces exposed in system, okay, we have to use the other strategies, such as, for example, maybe you can remember virtual work. Did you remember the virtual work theorem, or did you hear? I think you hear. If you don't hear, okay. If you didn't hear, I can explain in next week, and I think I'm planning to solve the question for virtual work and Castigliano theorem. I clearly in solving question. Do you have any extra question?
No question.
Okay, thank you, Berke, for answering. So I can finish my lecture. See you on next week. And I want to remind that if you have any personal question, do not hesitate to contact me as a Teams or email or any extra reaching platform. Okay.
Okay, thank you.
Have a good day. Take care.
You.
See you on next week.
See you hocam.
See you.
See you.